SwayamPrabha. Digital India. Educated India.
Well, I welcome you to the last lecture of week 6. The title of the lecture is Stepper Motor and Servo Motors. In this week, we are studying various electrical drives. So, let us look at the outline of this lecture. In this lecture, we will be studying the two important electrical drives. These are stepper motor and servo motor. We will be studying the principle of operation, construction and application of stepper motor and servo motor. At the end, we will have a discussion on the selection criteria. How to select electrical drives for the required purpose in building up an automated system. In this lecture, we will be studying two important motors. These are stepper motors and servo motors. Stepper motors are widely used in open loop control systems. The stepper motors are simply converting the DC voltage that is applied into a train of pulses, into a series of pulses. This pulse train is proportional to the mechanical rotation of the shaft. So the motor converts the DC voltage into pulse train, and that pulse train is making the rotation of the shaft. So this peculiarity of conversion from DC voltage to the pulse train is very much useful to consider the stepper motor as an actuator, as the energy provider, as the energy facilitator, as well as the position sensor. So we can consider that the stepper motor has integrated position sensing facility. The stepper motor is working based upon the discrete motion. It's not on the continuous input which is we are getting. So it is working based upon the discrete motion. It is creating the rotation of the shaft in the discrete way. Therefore, the stepper motors are very much useful when we are incorporating, when we are using microcomputers to control the system, to operate the system. Because as we know that microcomputers are working digitally, they also require pulses to process. Therefore, the pulse train facility or the utilization of pulse train based working of the stepper motor is very well suited for the microcomputers. The variation of the speed of a stepper motor is dependent upon the rate of pulse train input. As we are changing the rate of input, as we are changing the rate of the pulse train input, the speed is varying. On your screen, you can see the correlation between the rotational speed of the stepper motor in RPM as a function of the step angle, pulse frequency in hertz. The rotational speed of the stepper motor can be expressed in terms of a product of the ratio of step angle to 360 into pulse frequency in hertz into 60. What is the meaning of the step angle? As we have seen that the stepper motors are working by taking the input in discrete format. They are taking the input in pulses. For single pulse of application of energy, how much is the rotation of the rotor? That is nothing but the step angle. How much would the rotor will rotate in angular direction in angles? So that is a step angle divided by 360. Pulse frequency in hertz, how many pulses are being applied per second, that information we needed. So let us see a simple example. Consider a stepper motor. It requires 48 pulses to rotate through a complete revolution. To have a complete revolution of the shaft, we need to apply around 48 pulses. So when we apply 48 pulses, the shaft will complete the revolution of about 360 degrees. So for one pulse, it would be around 7.5 degrees. So that is the step angle. 7.5 degrees is the step angle. If we apply an input signal of about 96 pulses per second, so this 96 pulses per second is the pulse frequency. So let us multiply the 96 with 7.5 divided by 360 into 60. So that will come around 120 revolutions per minute. The stepper motor will have the RPM of 120 revolutions per minute. So as we have seen that in stepper motors, the rotation is basically carried out in finite increments, and these finite increments are of time. But if you try to notice these increments, it's very difficult. So visually, it's not detectable when the shaft is rotating at high speed. But if you reduce the speed of the shaft, then you can easily make it out that there is a discrete rotation, there is a discrete increment or discrete variation in the position of the shaft. The shaft is moving in increments along the angular direction. So certain characteristics, certain values are there in front of you. The stepper motors are capable of driving around 2.2 kilowatt of the load. Very huge load they can handle. In general, we can have a stepping rates varying from around 1000 to 20,000 per second, and we can have the angular increments from about 45 degrees to down 0.75 degrees. As the stepper motor is pulse driven motor, it is widely used in automation industry because we have seen its prominent advantages that it can considered as the position sensor as well. Based upon the number of pulses that we have sent to the motor, we can easily find out how much is the rotation. Stepper motors are having low cost and they are widely used in open loop position control systems. Basically, two types of stepper motors are being used: permanent magnet motor and a variable reluctance motor. In permanent magnet stepper motor, we are employing permanent magnet. They are useful for low speed applications, but they are capable of providing very high torque. As far as the variable reluctance stepper motor is concerned, these motors do not have in the permanent magnet arrangement, but they are providing low torque in comparison with permanent magnet stepper motors. So let us look at what is the meaning of, or what is the variable reluctance motor. The variable reluctance motor is working on the principle of magnetic reluctance. Magnetic reluctance is very similar, very analogous to the electrical resistance in electrical circuitry. The magnetic reluctance we are referring in magnetic circuitry. It is a ratio of the magnetomotive force, that is MMF, to the magnetic flux. The reluctance basically is representing the opposition of magnetic flux, and it primarily depends upon the geometry and composition of the object. On your screen, you can see the construction of a typical variable reluctance motor. It has a stator with number of poles. Here you can see around 6 poles are there, and we can consider them as 3 pairs of poles. There is a rotor, there is a typical rotor as we have seen in all electrical motors. There is a rotor stator gathering in the construction. The rotor also has poles. So on rotor we can see here there are 4 poles. The stator poles are having windings, electrical windings, and when we energize them in a sequence of 2, 3, 1 and so on, the motor will rotate in a step of 30 degrees step angle. In the non-energized condition, there is no magnetic flux in the air gap, as the stator is electromagnet. So when there is no energy there, when there is no electricity is applied, there will not be any magnetic power, magnetic flux. The rotor is simply a conductor. So at no load condition, at no electricity application, there will not be any magnetic flux in the air. This type of motor is called as the variable reluctance motor. In permanent magnet stepper motor, the rotor doesn't have any poles mounted on it. Instead, it is having a permanent magnet, but the stator is having number of poles. Arrangement of permanent magnet stepper motor can be seen on your screen. So there are 4 poles or 2 pairs and a permanent magnet rotor. So when we apply current to each phase in the sequence, that will cause the rotor to rotate by adjusting to the changing magnetic fields. So as we energize the windings of the stator poles in sequence according to the pulse input given by the microprocessor, the magnetic field will be generated. That magnetic field will rotate the permanent magnet. As the polarity of the windings is getting changed, the permanent magnet will try to orient according to its nature. If it's getting the opposite pole, it will get attracted to that particular pole, and in this way we can have the required rotation of the shaft. The permanent magnet motor are fairly having low speed, but they provide relatively high torque. The permanent magnet motor are quite economical. They are less expensive and they provide a step angle of about 7.5 degrees to 15 degrees. So we have seen there are certain limitations to the permanent magnet stepper motor and variable reluctance stepper motor. These two types of motors do have certain good advantages. These advantages are combined together and a hybrid stepper motor is developed. The hybrid stepper motor has the features of the variable reluctance stepper motor and the permanent magnet stepper motor. In the construction of the hybrid stepper motor, you can notice the rotor is a permanent magnet, and on the periphery of the rotor we are having teeth. The stator is as usual, it has number of poles which are energized by the electric current. These poles are having the windings, but here you notice there is a peculiarity. The stator poles also do have the teeth. So number of teeth or number of poles are provided to have the finer adjustment in the increment of the rotor. To have a very fine increment, to have a very small stepping angle, to get more resolution, to have a better resolution, we are increasing the number of the poles on the rotor as well as the stator. The working principle is very similar to the permanent magnet stepping motor. Here as well, we are energizing the individual windings in a sequential manner, and as the windings are getting energized, as the north and south poles are getting developed, the rotor will rotate to get aligned to the opposite magnetic poles. We have already seen how exactly the permanent magnet rotates due to the sequential energizing of the poles. So when a winding is energized, the north and south poles are created depending upon the polarity of the current, and these generated poles, they attract the north and south poles of the rotor. The teeth on the north pole would behave like a north pole, and the teeth on the south pole are behaving like the south pole. When the stators are energized, there would be major step increment in the rotation, but the finer adjustments we can do by having the number of teeth on the rotor. So as the poles are getting attracted to the opposite poles on the stator, the teeth on the rotor also are getting attracted to the stator, the opposite poles that is created on the stator. The construction of the hybrid stepper motor is complex, as it has a permanent magnet, it has parallel slots, it has teeth over its peripheral surface. Machining of the teeth is a very complex task, it's very precision task. In addition to that, we need number of poles, and these poles also do have the teeth. As the construction is complex, the hybrid stepper motors are expensive. These motors also require the electronic circuitry and microprocessor to control its operation. But these motors are providing us very small steps, that is the important advantage. They are providing greater torque and maximum speed. So we can easily compute the step angle in hybrid stepper motor by using this correlation. It is the ratio of two factors. First is the difference of number of poles on rotor and number of poles on stator into 360 degrees divided by 2 the product of number of poles on stator and number of poles on rotor. So on denominator we are getting the product, we are using the product of number of poles on the rotor and number of poles on the stator, while in numerator we are just having a product of the difference between number of poles on rotor to the number of poles on stator into 360 degrees. So let us take a typical example. On your screen you can see the number of stator poles are 8 and there are 3 teeth provided on each pole. So number of stator poles are computed as 8, that is a number of stator poles into number of teeth. The individual tooth is also considered as a pole. So number of stator poles are 8 into 3 is equal to 24. In a similar way, the teeth which are there on the rotor are also considered as the poles. They are the small poles or the micro poles. The number of poles on the rotor are 40. If we put these values in this correlation, we are getting the step angle of about 6 degrees. Let us take another example in which we are taking the number of poles on the rotor are 50 and we are increasing the number of poles or number of teeth on the stator poles. So by having 2 more teeth on the stator pole, we are getting number of teeth on stator as 40. We are increasing the number of poles on rotor as well. We are increasing number of teeth on the rotor as 50. So if you take NR as 50 and NS as 40, you can notice here we got a very good step angle, that is a 1.8 degrees. The prominent advantage of stepper motor is the micro stepping. As we have seen in a previous slide, the stepper motors or the hybrid stepper motor are able to provide around 1.8 degrees step angle to us. The stepper motors are having the low cost, they are rugged in the construction, they are robust in the construction. Some of the stepper motors are having simple construction. So there is low maintenance because there are no brushed contacts, there is no arcing or there is no wearing of the rotor or the stator. The microprocessor is controlling the energization of the stator coils. So there are less chances of having the slip or stalling of the motor. Stepper motors are able to work in any environment and they do have excellent start, stop and reversing responses. So we can have a very good reversing characteristic using the stepper motor. We can reverse the direction of rotation of the shaft with an ease. There are certain limitations to the stepper motor and these are the torque capacity of the stepper motor is less in comparison with the traditional motor, that is a DC motor. We are getting low torques, the power capacity is less and they provide limited speed. When there is overloading, the synchronization will be broken. So when the loads are too high on the motor, there may be chances of having breaking down into the synchronization of the rotor with the stator. And when we increase the speed further, that may lead to vibration or the noise during the operation. The next type of motor, which is very widely used in the automation, where we require to have the monitoring of the performance of the motor itself. Till now, we have seen that the electricity is applied to the motor is generating the mechanical power, but the rotation of the shaft is not getting monitored, it is not getting observed. Whether we are getting the required output or not will not be sensed or will not be taken into account. But in closed loop control systems, which are required in the development of automated products or automated system, we need to monitor, we need to get the information whether the required output is as per our standard. So the servo motors are providing this kind of facility. They are special electromechanical device. The special electromechanical device is called because they do have integrated monitoring system. Basically, the servo motors are DC or AC, or they are the brushless DC motor. So these DC, AC or brushless DC motors are combined with a position sensing device, and that position sensing device with appropriate signal conditioning device will give the input to the microprocessor, and the microprocessor is accordingly varying the input to the DC motor to get the required output. These motors are also called as the control motors because they are controlling the mechanical system. On your screen, you can see the schematic of the arrangement which is used in servo motor. We are having the servo motor which is providing the output. The performance of the servo motor is continuously being monitored, and the performance is given to the microprocessor or the electronic circuitry. The electronic circuitry is getting the input, the energy source, and that would be amplified and given to the servo motor. The input would be changed according to the error which is there in the comparison with the desired value and the obtained value of the servo motor. The desired value is the number of the revolutions per minute, and the obtained value from the servo motor, that is the actual or the real value which is we are getting at the rotor shaft. So what kind of positioning sensing devices are used? And these are the optical encoders. We have already seen the construction working and the application of optical encoders in the lecture of the sensors. Optical encoders are having the phototransistors. They are using the light and a perforated disc. As the light is passing through that perforations, it is sensing the number of pulses, it is counting the number of pulses, and based on that number of pulses, we can easily find out the angular velocity of the perforated disc. If we mount the perforated disc and a set of phototransistors, then we can easily have the continuous monitoring of the motor. And that is the arrangement is provided on the servo motors. The device is as usual providing us the mechanical motion, and there is an error detector which is just comparing the actual operation values with that of the reference input or the standard values. If there is an error, that error would be corrected in consultation with the microprocessor. In servo motors, we are monitoring the velocity and position. As we are monitoring the velocity and position, and we are online in situ modifying the velocity and position, the servo motors are providing accurate speed, torque, and they are having the ability to control the process directly. The first variant in servo motor is the DC servo motor. In DC servo motors, we are using a simple DC motor and a position sensing device. The DC operated servo motors, they respond very fast to the signal and they are able to accelerate the load quite quickly. A typical DC servo motor has four components, and these are DC motor, a gear assembly, position sensing device, and control circuitry. We have already seen the principle of operation of a DC motor and the position sensing device and the application of control circuitry. The next variant is alternating current servo motor, and in this case we are adding the position sensing device to an AC motor that makes the AC motor as the AC servo motor. So in this typical arrangement, the magnetic force is generated by the permanent magnet and the current arrangement which is producing the required torque. So as we know that there are no brushes in the AC motor, the noise would be very less. AC motor has better precision control and they do have high resolution. The AC motor may provide us better precision control when we are when we are employing high resolution encoders. It has the stator which is composed of the core and the winding, and the rotor is a shaft, rotor core, and a permanent magnet. So these details of the typical AC motor we have already seen in our previous lecture. So what kind of encoder we can use? So we can either use an optical encoder or magnetic type of encoder. These encoders are providing us the digital signals which are in proportion to the rotation of the shaft. The various advantages of the servo motors are as follows. The servo motors are providing high intermittent torque, very high torque to inertia ratio. So we can get a very good amount of torque in comparison with the inertia of the motor itself. The servo motors are able to provide very high speeds and we can easily control its velocity. The servo motors are available in all sizes. We can have a variety of sizes according to our requirement. They are quite in operation. The noise would be less, the vibrations are less, and they are smoother in rotation at lower speeds as well. However, they do have certain limitations as well. They are more expensive. So naturally, the construction comprises of the encoder device, microprocessor circuitry. The cost associated with the servo motors is quite high in comparison with the stepper motors. It requires tuning of the control loop parameters. We have to calibrate the servo motor quite often, and since the sensing circuitries are incorporated, since sensors are embedded, the servo motors are not suitable to work in hazardous conditions or in vacuum. When the temperatures are very high, when the environmental conditions are harsh, the servo motors are not suitable for such harsh conditions. In case of the excessive current, there may be partial demagnetization of the DC type of servo motor. So if you apply excess current, that may lead to the demagnetization of the DC type servo motor. That is one of the limitation. Till now we have seen various types of electric motors. DC motors, AC motors, we have seen the stepper motors and servo motors, their variants, their constructional details, and their applications in the automation industry. Well, when we are having many options in front of us, then we need to choose the appropriate one, a suitable one for our required purpose. The selection of an electric motor is very important as far as the efficient utilization of the electrical resources, that is the electrical motor. Though it is important, it is very tedious task. There are various factors associated with the selection of the electric motors. So some of the essential factors that need to be considered during the selection of the electric motor that we will see now. The first factor is the type of electric supply, whether we are considering utilization of a three-phase supply or a single-phase electric power supply, or we may have the alternating current supply or the direct voltage supply. So based upon the type of electric supply, we have to choose the appropriate electric motor. Next is drive variants, whether the proposed electric motor is being used to operate or to serve multiple machines by using a single shaft. So the electric motor is providing the input to a electric shaft, and that electric shaft is operating multiple machines through cams. So such kind of drive is called as the group drive. So whether you require a motor for such drive, then the consideration or the requirements may be different than the individual drive. So in the individual drive, a separate individual machine would be entitled for an individual process or individual operation. In certain cases, we may require multiple motors to carry out the operations. So based upon the type of drive, we can choose the appropriate electric motor. Next is electrical characteristics. So whether you need to control the speed, what would be the starting torque, what would be the stalling conditions. If you are working in a low speed domain, there may be chances of the stalling conditions. If you are working at a very high speed and then you have to just reduce the speed or you have to stop the operation, what would be braking characteristics. So the electrical parameters associated with the speed control, torque control, stalling and braking need to be considered when we select a proper electric motor. Mechanical consideration, the construction of the electrical machine itself. As we have seen that the electrical motor is an electromechanical device. So it is converting the electrical energy into mechanical energy, and the construction is very much important. What kind of bearings we are interested to have, whether it is a ball or roller bearings, those who are supporting the shaft inside the motor. The shaft is supporting the rotor. The shaft is attached to the rotor. Or we are using the bush bearings. If the bush bearings are there, then the friction would be more, the wearing of the shaft would be more. There may be chances of having the vibration and noise. Then the drives or the loading condition, where we are applying the mechanical energy. So are we applying the mechanical energy in a belt drive or a chain drive or a rope drive, or we are operating a gear based drive? What would be the loading conditions to this electric motor? These factors are also to be considered during the selection. What noise level we are expecting? If you want to have a very quiet operation, then you have to go for the AC drives or brushless DC motors. If the noise levels can be adjusted, can be accommodated, we can even go for the brushed DC motor because they are economical. We can save the cost, we can reduce the expenditure. Temperature conditions and heating, as we have seen that the brushed DC motors are having the heating problem. So can we utilize these brushed DC motors in harsh conditions where the already temperatures are very high? So the surrounding temperature conditions are also affecting on the selection of the electric motor. The service capacity, we need to take into account for what duty, for what type of duty the electric motor is being applied. Whether the electric motor is being continuously utilized for the operation, or they are used for a short time duty, or it may be a intermittent type of operation as well. The rating, many manufacturers or there are standards available, those who are computing the rating based upon the utilization of the electrical energy, voltage, current, the speed characteristics, the characteristics related to the excitation, the torque stalling, efficiency of the drive, and the power which is coming out. Based on that, the ratings are decided. During the selection, even we can give focus on the rating, and based on the rating we can choose the appropriate electric motor for our purpose. Appearance, so this is very important nowadays. Aesthetics, how the motor construction look like, whether it is suitable, this may be useful. The appearance would be very much essential when we are using such drives to make the robots, or we are making the gadgets or the toys. The cost consideration, that is the most important. The, the electric motor should be cost effective, less expensive, and they should able to satisfy all requirements of the designer or the end user. So let me summarize the lecture 3 of week 6. In this lecture we have seen two important electrical drives. These were stepper motor and servo motor. So we learned the principle of operation of these electric drives, their constructional details and applications in the automation industry. At the end of the lecture, so we have carried out a discussion on the selection criteria, how to select an electrical motor for the required purpose. In the week 7, we will be studying the various mechanical systems or mechanisms which are required in the development of an automated system. In the lecture 1 of week 7, we will be studying the introduction to mechanisms, a detailed discussion on the constructional details of the ball screws, their advantages will be carried out. We will see about the linear motion bearings, various types of cams. Cams is a very useful mechanism and it is widely used in the automation industry. There are certain systems which are controlled by the camshafts. Some of the systems we will study in this lecture. With this I conclude for the week 6. So overall in week 6 we have seen the requirements of various drives in automated system, and then we carried out the discussion on various electrical drives. We saw the DC motor, AC motor, servo motor and stepper motor, 4 prominent types of motors which are used in automation industry. At the end we studied the selection criteria, based on that how to select an electrical motor for the automation purpose. Thank you, goodbye.